So before I get started, I know it's been kind of flipping through. Did everybody maybe catch the cartoon? Everybody got that? What we're about to talk about today doesn't just apply to our industry. This is pretty much any new emerging technology, whether it's Bluetooth in this case, or anything that comes out. It's just a reality of how technology gets implemented and how technology changes as we go. And so when I was talking to Bob and Tim about a week or two ago about what we wanted to talk about, I said, you know, Robert, you've been out in the field quite a bit talking to customers, and you've been doing a lot of these IP installs, so what have we learned? You know, we've been doing them now for about 5 years now for IP installs, and SMPTE 2110 came out just over a year ago. That was IPC last year. So what have we learned? And I thought it'd be a really good topic, because a lot of this stuff, we're going to talk about technology a bit, and for the 1 hour window I have, I try to cram in as much data as I can. So I pulled out my usual comics and my usual fun drawings, so I'm sorry if it's going to be a little more dry than my presentations are, but I wanted to kind of get the data through. So, what have we learned? First part, I hate to say it, it works. If you asked me 2 years ago, I would have said that. If you would have asked me 2 years ago, I said, yeah, it works in the lab, or it works in the field under very particular circumstances. But I would definitely say in the past 12 to 18 months, we've had hundreds of deployments on the air. This isn't just the Grass Valley, hundreds of deployments. This is between all the major manufacturers that have been working together to make this a viable solution. So we're to the point now where it finally works. The thing I like about seeing that it finally works is how many people here have sat through what is SMPTE 2110 or what is PTP? Everybody probably sat through one? How many people have sat through a presentation of, okay, we got great technology, what can we do with it? Nobody raised their hands, everybody laughs. That's the exciting part about where we're at now. We have proved that the technology works. We have the technology in the field. Unfortunately, most of the jobs we've done so far is we're just taking existing workflows and making them IP. Well, what does that buy you? It buys you some scale. We can make things bigger. We can do bigger facilities now. Buys you a big, pardon the language, buys you a big pain in the ass. So what does it buy you? So to start off with, one of the first things I can definitely say is now that we have the tool set to do workflows in a whole new way, why are we still doing the same workflows? Something to think about. I don't have an answer. Well, I do, but this is kind of what our company does, and I can't tell everybody what we do. Another part is I've got 2 case studies queued up. And one case study, we started the job about 5 years ago, and we went on the air last year. Or actually went on the air in the last couple of weeks. We started the build up last year. Another one we started designing last year, and we brought on the air about 4 months ago. And what we found is technology is advancing faster than the projects can keep up with. Well, what does it mean? Well, if you've seen any of my presentations in the last year, there's been a 100% chance this slide has been in it. And this slide to me speaks a lot of what's happening in our industry. And when I say our industry now, I'm not just talking broadcast, I'm talking about media. Moving bits from point A to point B. And what's interesting is, you start, I forgot if this is a projector, not an LED wall. Started in 1980, 10 megabit. Then we went to 100 megabit, then 1 gig. By 2000, we had 10 gigabit. It's not a bad jump in speed. As of right now, we have 6 new speeds coming. So instead of 1 gig for a base frequency, we've got 2.5 gig. Native 5 gig is coming. Pretty much everybody now is doing native 25 gig. When I first started using the slide about 1.5 years ago, I was saying that 25 gig is going to get popular. We're past that. This is a 1.5 year old slide. Now 50 gig is starting to get popular. Now to get to 50 gig single pair, you have to have a whole new way of modulation. And so that's been a whole new technology base to support 50 gig data rate. Another thing that's shipping this year is switches that have 36 400 gigabit ports. Now, a 36 port 100 gig switch is equivalent to an 800 by 800 3 gig router in 1 RU. Now we're doing it by a factor of 4 larger in 1 RU. So the bandwidth is there. The bandwidth is there to do some really cool stuff. So the first job we designed, then the first case study you're going to see was based off of a 10 gigabit interface with 40 gigabit uplink. Because when we started design about 5 years ago, that's the best technology you can do that was affordable. The second job we're doing is going to be 25 gig at the edge and 100 gig uplink. We're already starting to design projects today that are 50 at the edge, 400 gig uplink. That's changed in 1 year. It's not going to slow down. So, what does that leave you? It requires a whole new kind of engineering. And this is the part I want to talk about before any technology, is the biggest problem we're having is the human factor. And this isn't just a customer problem. This is a Grass Valley problem. I know we got a couple of Grass Valley people in the room, so I'll pick on you since, well, I'll have to see you eventually, which is hopefully you have to be nice to me because we're in the office. Luke, how many people on your team have in-depth knowledge of SDI and IP knowledge? They know how to configure Cisco switches. They know how to handle DC and M. They know how to handle multicast, unicast flows in a broadcast environment.
With any depth to the knowledge?
Yep.
Probably less than 20%.
That's pretty, and by the way, I did team up for that. That's actually a pretty consistent number we're seeing. Is about 20 to 30% of the broadcast engineers, both in the vendor space and on the customer side, are having this problem. If you have an engineer that spends all of his time learning SDI, how does SDI propagate through an environment? And then all of a sudden you say, you know what? I don't care about SDI. All of my video, all of my audio is now a function of bandwidth. That's it. All of that SDI knowledge they have more or less goes away. But we still do SDI today. So having an engineer that understands SDI to the depth and level that our customers need to know and that we need to know is important. But also our customers and we need to learn switch configurations. What is unicast? What is multicast? What is DCNM? What is SDN about? IGMP, and even the standards. Why does the standards really matter? Most of our customers don't care that SMPTE ST2110 was your SDI standard. Why? Because they plugged the stinking cable in and it worked. It's not the case anymore. Take it a step further. Now you have to know for the future. Because as we just showed in the previous chart, the technology is changing faster than it ever has before. So if I build a facility for today's technology, by the time it's deployed, the technology is already behind the curve. So now the engineers not only have to know about SDI and networks, they have to know about what's coming through in the future. So they need to know stuff about AMWA and JTNM and IEEE and Streaming Video Alliance. Basically, they need to know this. And if you guys haven't seen this, it's the JTNM roadmap. And every technology we've been through the past 5 or 6 years has been on this chart. You know, we started off at the very bottom of 2022-6. And we've been kind of working our way up the stack. Now that 2110 is solid, we don't really worry about this too much anymore. So now the biggest problem is how do you control it? Well, that's this whole part. And the next biggest part is how do you secure it? That's the huge part. Between JTNM, SMPTE, AMWA, EBU, and I think there's other standards, we're going to have 5 different technical security recommendations in the next 6 months. First off, which one do we choose? Second, how do we make them all kind of work together? And that's kind of what JTNM's doing. But we're going to have a lot more data coming out. So the engineers today have to understand this roadmap. It's not as simple as it used to be. The last thing is, we still have a lot of work to do. Anybody here heard of a JTNM full stack? 1, 2, well, we talked about the lunch, but right now. So 3, 4, a few people have heard it. So what the JTNM full stack is what is a recommended practice for my entire broadcast environment that pulls together addressing, name resolution, standards, control, security. It's basically this entire profile of how you should build a facility. It hasn't been released formally yet, but there's beta versions kind of running around. So if you guys have any engineering guys or ladies, my apologies, have contacts in your facility, feel free to reach out to them. Somebody may have a copy of it. We can't give it out publicly yet because it's not published yet, but it's something good to know about. And security implications. So now that your IP, now that your video is a function of bandwidth, how do you secure it? We didn't have to worry about an SDI, because how are we going to route an SDI signal out over the internet if somebody hacks your facility? Don't have to worry about it. But now that your video is a function of bandwidth, bandwidth is cheap. It's very possible and very real that could happen. But think about it even more. ISO 5, the AMWA standard for control. ISO 5 is an API that allows any device to be controlled by any SDN controller over an open API. Cool idea. We need it. how do you secure it? What's to keep me from plugging into a laptop and saying, you know what, that transmission server, I'm going to send you an ISO 5 join to my source that I want you to join, even though it's not approved by the rest of the facility. It's a real challenge you have. Or what's to keep somebody from flooding your PTP and knocking your reference clock off your entire facility? I think everybody here knows broadcast TV doesn't work very well without reference. So there's a lot of stuff we're having to look into, is security implications and what are the best practices. Because you don't want to go too over the top of security because then you can't get work done. So on the generic side, that's where we're at. But the biggest part is we've got to start having fun with this. We have a new technology tool set that allows us to do workflows we've never done before, yet we're still doing the same workflows. Let's break some eggs. Let's try having some fun. Let's try to do some new technology. Because that's what these tool sets allow us to do. Most existing builds emulate traditional workflows. This first case study I'm going to show you is the exact same workflow if we did it on SDI, just on a human scale. Doesn't really bias the advantages. And start designing the workflows leveraging new technology. How do you do it? Well, since most of us here, I think all of us here are vendors, that's our revenue model in the future. So stop doing things that we've always done, find new ways of doing it. And hopefully I just didn't give anybody encouragement to sell better products in Grass Valley by saying that. All right, so any questions on that before we dive into the first case study? All right, awesome. So the first site we did was WCAU in Philadelphia. This is an NBC-owned station in Philadelphia. And they, we started the project about 4 years ago, 5 years ago. What the idea was going to be on the air about a year and a half ago. Thankfully, not for technology reasons, but the building wasn't built yet. They got pushed about a year and a half. It's actually built in the big Comcast tower in Philadelphia. And Comcast said we wanted to demonstrate the broadcast facility of the future. We want to go all IP. We want to get rid of all of our traditional infrastructure. We want to get rid of microwave. We want to get rid of whatever. We want to go all IP. That was our goal. So, remember we started designing this about 5 years ago. 5 years ago, there wasn't SMPTE 2110. 5 years ago, you had 2022-6. Doesn't really get you what you wanted to go. Now we have the recommendation of TR04, which is 2022-6 video with AES-67 audio, as separate media flows. So that's what we did. But how do you design a facility for a technology that doesn't exist yet? That was our problem 5 years ago. And this problem will continue being a problem. We will always be designing new facilities for technology that may or not exist yet. At that time, we didn't even have standards. So that was one of the complicating factors. So the challenge the customer gave us, design infrastructure for a top US market. The only reason to put that on there is they wanted 5.9 uptime. That's written into the contract. So that's, for those of you who know the nines of uptime, it's between 4 and 6 seconds a year of downtime. That's what 5.9 gets you. So to kind of put in bigger clauses, are you guys okay not having electricity 99%, or having electricity 99% of the year? That's no nines. So anybody that says yes, you don't have power for 3.65 days out of the year. So 99.9 is better, 99.99 is better, so we went for the 5.9. That was the customer's requirements. Because of their contractual agreements, they want to use Cisco switches. That's one of the biggest things we've run into is customers say, what works best for you? We say what works best for us. Well, great, there's other vendors who we have a contract with, so make it work. Well, why did you ask us in the first place? But, so we run into, because this job was done so long ago, 2110 didn't exist. So one of the things they wanted is, I want an infrastructure that is flexible enough that we build it with what's existing today, and in the future, through a firmware upgrade or software upgrade or whatever, we can go to 2110. We're still at TR04 on that facility. Because it is built off a couple-year-old gear, the reference is mixed. It's not all PTP, it's not all black, it's both. Some of the older gear that was SDI that has to be converted to IP still requires blackburst. Everything that's IP has to have PTP. Sir?
Tell me what TR04 means.
My apologies for that. So TR4 is a technical recommendation that was based out of the JT&M. And they JT&M went with this kind of walk, run, sprint idea. And to first get video into the IP domain, we're just going to take that video as exactly as it is on a coax, and we're just going to wrap packets around it and send it out the door. So that's 2022-6 video. But there's a problem with that, is when you just treat your video like you always have, your video is embedded into that stream, but your audio is embedded in that stream, and your metadata is embedded in that stream. So I've got my video as IP now, and my audio is embedded in it. If I want to route my audio somewhere else because it's an IP, I have to first encapsulate it in a hardware device, then I have to deserialize it, then I have to do my audio routing, then I have to reserialize it, then I have to repacketize it. So it's a total pain to route audio separate from video using 2022-6. So TRO4 was kind of the first thing of what we call essence-based routing, where video has its own stream, and audio had its own IP address running as its own separate essence. So now video and audio are separate. It's not quite as full as SMPTE 2110, but at the time is what we could do. So TRO4 is exactly that. Signal agnostic. The biggest thing we ask our customers today, what format do you want? Yes. Okay, same question. What video format do you want? We don't know. We want it all. Okay, so remember, when you see things like this, that the media is now a function of bandwidth. So if I build a facility for 10 API, I'm going to build everything for 1.5 gigabit per second flows. But if the customer says, I might go UHD in the future, I might go 4K, well, now I have to build every flow as 12 gigabit instead of 1.5. So now I have to allocate almost 10 times as much bandwidth for something they may or may not use. And they're going to pay for it. So if you want to pay for it, let them. Future ready HDR doesn't scare us too much. 1080p compared to UHD is nothing, it scares too much. The other part is simplified wiring. They want multimode or single mode fiber. They want to get away from coax. And when you can see the reference to top of rack of end of row, top of TOR, or EOR, just gave it away. TOR is top of rack, and EOR is end of row. So what they did is they have a network switch at the top of every rack. And they have a bigger switch at the end of every row. And I'll go to some drawings of that. The idea being you're never pulling coax or fiber in a rack farther than just to the top of the rack. And then you have a big bandwidth fiber going to all the rest of it. 3 studios, as much IP as the edge as possible. Again, this was built roughly 4 or 5 years ago. There wasn't a lot of IP at the edge, basically native IP devices then. Now, pretty much everybody has native IP devices. They had a traditional SDI switcher, huge multi-video requirement, we'll go into that in a little bit, plus mass control, plus live production, and all the audio video processing you need for a station, plus remotes. This is a full-blown top 10 market station that wanted to go into it for the first time ever. And they wanted distributed IP infrastructure. And this is one of the big workflow parts that really, really helps with IP. And it's not workflow in terms of the users, it's workflow in terms of the engineering. When we did SDI routers, we took every cable, every source, every destination of the facility, and we ran it all the way to one box in the middle. It's a lot of coax. Our parent company spelled it. Okay. But that's not exactly what the industry wants. So how about, instead of running a whole bunch of coax back to one box in the middle, if I've got 6 or 7 or 8 satellite receivers next to my satellite dishes, how about I just put a network switch there and pull a couple of fibers back? It makes the wiring significantly easier. The other thing is to span multiple floors. The nice thing about getting away from SDI is distances you don't really care about. If I want to go a couple of kilometers, 10 kilometers, 100 kilometers, single mode fiber. If I want to go 500 meters, like a multi-mode fiber, it just takes it off the table. You don't have to worry about that anymore. And also multiple sites around the facility, or the city. Both uncompressed and compressed, multiple codecs. But remember, who cares if it's compressed or uncompressed? It's all just a function of bandwidth. But this is the big part, and you'll see this in every slide I have. The users don't want to know it's IP. The technical director punching the show, his job is to create the most dynamic and engaging content he can do. If he's worried about an IP multicast flow for a source, he's not doing that. So the hardest part of the job was hiding the technology from the user. We like to use the phrase internally, the best product we can make is when our customers don't care about it. It's true. If our technology is seamless and allows them to do the creative job they can, what do we care? So for those who are big in the Cisco world, we used Cisco DCM, which is kind of their SDN layer. Multi-spine, I'll give some drawings on that for those who don't know it, for multi-spine or multi-leaf. And it's also redundant. How many people here have had a network switch die? Probably somebody, 1, 2, 3 people. Well, our customers, about 100% of them have a network switch die. Do you want your entire facility to go off the air if a network switch dies? No. So how do you do it? You just build 2 networks. There's no way around it. And that's the 2022-7XY design. This is a Grass Valley plug. We'll skip that. Sorry. So the network topology. I'm sorry for the people in the back. If you want to come forward, feel free to. So this is a high level. So we have, what we're looking at now is 3 main networks. There's actually 4 that we kind of buried in there. So we have what's called VLAN. This is your broadcast LAN. This is your traditional broadcast network that we've always had for the past 10 or 15 years. That's how to tie gear in together for configuration and management, and status and health and all that kind of stuff. That's your typical 1 gig LAN done. To do that, they use the big spine system. But the big part is the media LAN. So media LAN X and media LAN Y. The 2 networks are identical. Multi-leaves, multi-spines. The idea being is every source in the system feeds both networks. And every destination pulls from both networks. If one dies, you have the redundant layer. Good to go. Then they did a lot of stuff in this facility because we've never done it before that we wouldn't do it again today if we had to. I'll show the next on the next slide. Whenever customers get nervous about new technology, they always tend to overbuild. And this job is definitely overbuilt in some aspects. So I told you we had 2 X and Y networks. This is one of them. So what it is we have 2 spines that connect all of these switches together. And in each one of these switches is all the different 10 gig and 40 gig connections. So what you're seeing is kind of the hierarchy tree of the facility. Their facility was so large. By the way, it's about 1,700 sources and 1,400 sources, 1,700 destinations. So it's a pretty big facility. We couldn't do that over 1 core switch, so we had to go to multi-spine. So that's what you're seeing here. But one thing we probably wouldn't do again is this bottom part. This diagnostic LAN. The customer wanted the ability to tap into every single switch without using the SDN layer. So if they want to do some like diagnostic steps or anything like that, that they can do that with removing the SDN layer out of the system. The reality is this system won't work without SDN. So if your SDN's down, you testing of a single point in your facility is pretty much superfluous because you don't have video on the air. So this is one of the parts that they overbuilt. And this is about a $200,000, $300,000 overbuild on their part. This is them using traditional methods for new technologies, but it's the first time they've done it, so they're scared. Another Grass Valley plug, apologies. So here's the part that's incredible with this. Their parent company is Comcast. And so they wanted to get away from using microwave for their microwave receive sites for the live trucks and for the satellite farm. So the customer goes to Comcast and says, hey, we want to get away from microwave, we want to go to IP. Can we get a couple 1 gig links between our facility and our microwave receive site, which is about 4 buildings down? Can we get a couple 1 gig links from our building to the rest of our microwave receive sites? There's about 6 or 8 around there. Comcast is like, you know what? It's actually just as much pain to give you 1 gigabit as it is 100 gigabit. So we'll just give you redundant 100 gig paths across the entire part of Philadelphia. For those who don't know, that's about $1 million a year in internet data costs for the lines, the setup, all that kind of stuff. If you own the fiber, it's not, but they don't own the fiber, but when your parent company is Comcast, it's literally as easy for them to give you 100 gig as it is for 1 gig. So when you pay your guys' Comcast bill, remember that. So we had 100 gig media trunks to all their remote facilities. And the thing is the remote facilities use a third-party switch. So we had another vendor we had to work on here. So this was kind of it. Again, you notice full redundancy, multi-leafs, and you got multi-paths going to all their carrier switches. So I didn't show all of them. You only see 2 of the 100 gigs. They actually have about 1,800 gig connections tying all their facilities together. So if you want to truncate that, they have 1.8 gigabit of data, or terabits of data that they're using just to do microwave shots. The duty cycle is about 2%. But it was free, so why not use it? So again, although they went way over the top with the bandwidth, this is another good example of using technology the right way. Let's use technologies to connect things over IP pipes when we can, instead of having to use traditional microwave. Now they're not using this microwave for STLs. They can use those same microwave frequencies to do more live shots. They can generate more content. They can generate more live shots. They can generate more edits. So this is using technology the right way. How can you enable the technology to give you a better end product? So SDN's important because they happen to use ours. But when you make a route in the IP domain, what you do is you tell the end device. Let's say I'm a replay server. My replay server says, could you please send me the video for SAT1? Well, the video for SAT1 is actually 239.1.17.236. The audio is going to be 239.43.16.197. I'm making them up. But you can't let the operators know that. The operators just want to be able to poke SAT1, replay 1, take. So when you see the SDN control layer, at the simplest factor, it just converts all the IP addresses that are in the background to human understandable nomenclature. That's all. The other thing is high-level topology view, so we can kind of diagnose stuff really quick, and we'll dive into that here in a little bit. Security was a key principle. We wanted the ability so nobody could just plug into the network and start doing nefarious things. So the way the network's designed is it has a default deny access control list. Every single port on that switch is dead until you give it permission to come alive. But even though the port comes alive, it still won't come alive until the MAC address is correct, the IP range is correct, the gateway is correct, all this different security checks. So that's a very easy and a very fundamental security that you can build in the network that just keeps people from doing stupid things, whether they're allowed to or they're not. So again, my apologies for the people in the back. This is the topology view of the facility. Again, this is using the SDN layer that the customer chose. So what you're seeing here is you're actually seeing here's a bunch of monitors, a bunch of endpoints. Each one of these is kind of broken down into frames, what their function are. This kind of tells you the wiring for the entire facility. But although this looks really, really busy here and kind of gives you a headache if you stare at it too long, there's some pretty important stuff that comes from that. We've already identified that of any traditional facility, only 20% of the users will truly understand the technology, right? Probability of an engineer at 3 o'clock in the morning who is just pulling the overnight shift, running into a problem and not knowing how to diagnose IGMP media flows through SDN infrastructures, leveraging Cisco DCNM with their Grass Valley convergence system on top of it, it's about 0%. Right? Do you guys maybe agree? So you have to build tool sets that break this incredibly complex technology down into simple things that people can understand. So an operator says, I went to this source to this destination and it didn't work. Cool. That's awful. Let's figure it out. So the first thing you got to figure out is what's the physical connection? What wires does it take? Did somebody unplug an SFP? Did a fiber get crushed? Did a switch die? Whatever. So what we're actually seeing here is we're seeing a source, and the source feeds a gateway. So it's an SDI source feeding the gateway, even shows you the cable, shows that it's going into input port number 1. Output of that gateway feeds your redundant networks. So through that network, you go through 3 switches. You have a leaf, a spine, then a leaf. Then you go back to another converter that converts IP back to SDI, and then SDI to your destination. So if you have a flow or a media that's going from one source to a destination and isn't working, this tells you where it's not working. Because I did this on my laptop, that wasn't connected on an airplane, everything shows red. In reality, this will be black if it's fine, it'll only turn red whenever there's a fault. So this allows you to very quickly see where the physical fault is if it's a physical fault. So these are some of the tool sets that are really, really key because not all the operators know the technology as well as we do. So, what else did we learn? PTP is awful. For anybody on the technical side, PTP is just a total pain in the butt. A lot of it's because we didn't know what we were doing. PTP is based off of the SMPTE standard, which is called SMPTE 2059. SMPTE 2059 is actually based off of an IEEE standard 1588. IEEE 1588 has been around for ever. Sorry, I'll stay over here so I don't. It's based off of an IEEE standard 1588. IEEE 1588 has been around for decades. Power grid, all PTP. If you have a cell phone that's based off of digital technology, so every cell phone, that's all PTP. Because you have to have hyper-accurate, especially in the TDM networks, you have to have hyper-accurate spacing of your RF and your packets to the network. Industrial automation, PTP. This isn't new, but it was new to the broadcast. And as you guys know, the TV industry has a habit of taking an established technology and making it really complex. And SMPTE did a fantastic job with SMPTE 2059. They did what we had to do, but it's definitely more complex than your traditional PTP installations. So the other part is you can't use your traditional vendors anymore. And this is coming from a Grass Valley guy, by the way. Just because a company that you use a reference generator for the past 20 years has been fantastic, doesn't mean it's going to work now. Doesn't mean it's going to fit your workflow now. Because we're now using technology that other industries use, there's newer PTP generators that we can use by different manufacturers that in many ways work better than what's already out there in the broadcast domain. And I'm not going to throw any vendors under the bus on this one, but we burned, I'm probably going to say almost a man a year of staff over multiple months on site because of a bad PTP generator. Just causing all the video and audio in the entire facility to break up. And it only happened once every 7 days, and it only happened for about 20 packets. But are you okay if your TV station doesn't have video for about 5 seconds every 7 days? So we had to find the problem. The problem was the clock generator. And even though the vendor said that this is fantastic, this is a great build, no. We pulled them out, put a different vendor in, that problem solved itself immediately. I mean, we had hundreds of thousands of dollars in man hours invested in this. And it wasn't just Grass Valley, other vendors were there, other companies were there, and it was awful. So just because a vendor has worked in the past doesn't mean they're going to work in this environment. Another part, we're going to go into some drawings on why. Most PTP clocks made by traditional vendors give you one PTP port per clock. And we'll on the next few slides, we'll talk about why that was bad. And this site, on hindsight, PTP was way overly complicated. We could have done this way easier. But again, it's the first site ever like this of its size using this technology ever, so we over-engineered. So what do we do? So this is a high-level PTP design for their site. So you have your two PTP generators. By the way, PTP supports almost an infinite amount of PTP generators, so you don't have to just settle for 2. You can do way more. I actually recommend at least 3 or 4. Compared to the cost of the rest of the facility, the cost isn't much. So remember how I told you that the PTP generators only have 1 port per generator? Well, I need a generator to feed 3 networks, but I only got 1 port. So what do I have to do? I had to buy another set of switches, these 2, dedicated to distributing PTP. Well, anytime you add more gear to an equation, you also add more instability to the equation because it is inherently more complex. There's more things to fail. So this added a whole other abstraction layer that could fail. And it's in the worst place possible. It's in your reference bus. So where do you not want that complexity? Reference, because that affects your entire facility. So what you see is the PTP generators come to these 2 switches. You notice there's always 2, no single point of failure. It feeds each XOY network twice into 2 different switches. What's the point of having redundant PTP if both PTPs come into 1 switch and the switch dies? You still have no PTP. So you have to look at redundancy on a whole new scale. So PTP is mandatory for the media networks. For the SMPTE 2110, the TR04, it's absolutely mandatory. The broadcast LAN, it's not needed. You know, for command and control and configuring, most things in the broadcast LAN today don't need it. So why do we do it? Honestly, it was for the cost of a couple 1 gig ports or a couple 10 gig ports, which is about $300. Why not? You may need it in the future. Would you rather have it now? and be ready for it in the future, or in the future find out you need it and you didn't prepare for it. So for the cost of $200-300 ports, just throw it on the house land. That's what they did. So to me, the part that was really over-engineered was this. Didn't need that extra layer of abstraction. This comes back to buy from the right PTP generator. There's your time shot of it. So both of these switches here, and all the cross-connect and the programming and management that comes with it, could have been gone if we just went with a non-traditional broadcast vendor. So here's what we're seeing from the PTP network connected into one of the XYs. Remember, they're redundant. They're exactly mirrors, so whatever we do on X is going to be done on Y. So I just showed this one side, but you can see what's coming into 2 different leaves. Again, for redundancy. And again, redundancy to the broadcast lane. There's no single point of failure in this entire facility. Not one single power supply can take it off, not one SFP, not one SDM layer. There's not one thing in this entire facility can go down and take the whole thing down, unless the building burns down. So your largest failure block is the building, physical. That's it. That's how you have to design it. So, talking about on the detail side real quick, is the way PTP works is you have your PTP clocks. In this case, we have a Tech and a Meinberg. By the way, both of those clocks, pretty solid. Tech only has one port, the Meinberg has a whole bunch of ports, really awesome. So these are the 2 that we ended up putting in here to pull the other vendor out. So the way PTP works is your generators send the PTP signal to your network switches. And then your network switches take that's what's called a boundary clock, and it pushes those clocks down to all the slave devices that are into it. So really all it is the PTP generators are just locking these guys to hyper-accurate time, and these guys are distributing the time to all the other devices. So let's talk about some lessons learned here. So remember, everything's X, Y. We have 2 of everything. So we have PTP going in X, and PTP going into Y. What happens if for some reason Y's clock drifts, but X's doesn't? So now you have a delta in your time. What do you do? Well, with the first version of Cisco code, you just crash and the whole switch shut down. Not really good for the broadcast facility. So we kind of fleshed out some bugs there. So other things is, okay, so these guys now have a clock in them, and its clock is continuously syncing off of these PTP clocks. If for some reason, say somebody during commissioning unplugs the PTP generators. So the entire facility is running off of a free run based off of the Cisco switch. What happens when you bring GenLock back in, or in this case reference PTP back in? There's going to be a bit of a delta. Your switches are going to be a couple milliseconds ahead or a couple milliseconds behind GPS time. So what do? Well, with Cisco's new code, they just did a giant jam. And for anybody on the switcher guys know exactly how bad that is, but when the switcher timing windows are so small, that caused the video to break across the entire facility. Only for a couple frames. Still pretty bad. So Cisco had to go back and rewrite their code. When you see a delta between your grandmaster clock and your boundary clock, do an incremental jam. Just do a couple milliseconds, microseconds here or there, instead of just doing one big giant jam and bringing it all together. This is a lot of the little stuff we've had to go through, which is finally out of our hair. But this facility is where we discovered a lot of them. The last part to talk about, how about audio? Is there any really hardcore audio people in here? Nobody? That's a lost art that nobody cares. One guy?
I'm analog.
Oh, analog audio. Well, okay. I'll give you the respect for that. Audio is the hardest part of this entire facility. Video is easy compared to audio workflows. And there's an interesting interop point in this. So the Grass Valley, we chose to use SMPTE 2110-30. So -30 is the audio component of the 2110 standard. Level C, which is 16 channels per trunk. So 16 channels per IP address. Your packets come out every 125 milliseconds. Some of the other vendors only support in level A, which is 1 millisecond packet timing and 8 channels per trunk. That's actually a really big interop point. If I'm trying to send 125 millisecond packet timing to 16 channels to a device that only accepts the slower packet timing and less channel count, what's going to happen? Nothing. That's exactly what happens in that case. So this became a big interop point. And to the point, SMPTE has actually spent a ton of time, for our sake of time, I'm not going to go through all of them, saying what is the level A, B, and C of SMPTE 2110-30. We knew this going into it. Because nobody had done this before, we didn't know that we had to go through every single stinking piece of gear in that entire facility all 1,400 of the sources and all 1,700 of the destinations to make sure they conform with both A and C. Because SMPTE says you only have to do a level A. SMPTE's phrasing is, every device to comply with SMPTE 2110 S30 shall comply with level A, should comply with C. It's one of those little minor differences that can really burn you. Get on this one. So this is the last part of it for this case study, is a lot of work went into programming the system. There is no ISO 4, there is no auto discovery of resources, there is no ISO 5, there was no open API between everything. All unicast addresses had to be static. Fine. Well, I had 1,400 sources, so somebody had to write 1,400 static IP addresses into that on the source side, and 1,700 unicast on the destination side. So roughly around 2,000, because some of the devices overlap, some devices are bidirectional. So we, as a commissioning company, had to go in and write 2,000 unicast addresses. We're not perfect. We messed up. We got some IP addresses wrong. Just an accident, it's a human factor. That's one of the biggest problems, is how do we remove the human factor? Because at this point, the sheer numbers we're doing is terrible. But here's the other part. Because every source flow has 2 IP addresses, one for the video and one for the audio, you have 1,400 sources, so that's 2,800 IP addresses for multicast. Again, we made mistakes. But here's the other worst part, is every single time you add a new source to the system, somebody has to IP it. And at the time, the industry didn't support DHCP for any of this. We still don't. This whole full stack thing you heard me talking about earlier is starting to push DHCP and automatic registration. So that was a really big issue for us. Sir?
How did you do the split of the addresses when you went to the redundant?
So that site was subnet plus 1. So one was 239.0.0.0, the other one was 240.0.0.0. We've seen a whole basket of them. Some customers want both the same IP addresses, which I think is kind of mental, but you can do it because they're full XY. Here's another consideration. This is just kind of tangential, but it's a good thing to know. Imagine you're NEP and you have an IP truck. And your entire truck is 239.0.0.1. And you're doing the Super Bowl, so you have to work next to a Game Creek truck. So you're going to pull some 100 gigs between them. Well, what happens with a Game Creek truck is IP 239.0.1.0.0.1. Like earlier, nothing, everything crashes. So the truck manufacturers, the big ones, have all gotten together and had this kind of common accord. Game Creek is going to use this subnet, NEP is going to use this subnet, Colorado Studios is going to use this subnet, Lion's going to use this subnet. They just kind of did that on their own. Not official, they just did it. But these are some of the things you have to consider now that we never really had to work before. It used to be, we just did a trunk of SDI or trunk of fiber between them and called it done. It's just a lot more data you have to go through. So, questions on that before I jump into the last one? By the way, this one goes a lot quicker. Sir?
It's probably a dumb question with a simple answer, but you mentioned that GB Convergent was responsible for setting up all of the routes.
Yes.
So I would assume you have an open API that allows other vendors to talk to GB Convergent?
That is a good assumption.
Okay. How do you secure that API?
That's an even better assumption. So, in the early days when this site was done, there was no open API. Now, we were willing to open up our code so somebody could write to it, but the vendor had to do that. So the whole push between AMWA, ISO 5, I saw a couple references to that, that's that open API. So AMWA ISO 5 is an API that the SDN control layer writes to, and the edge devices write to, that it doesn't matter what vendor it is, as long as both vendors are writing to ISO 5, we now have an open API. That didn't exist when we started this job. And your other point about how do you secure that endpoint, that's huge. That's actually what full stack and security is trying to address.
Okay.
Because to his point, if I have an open API that anybody can write to,
Yeah, so secure.
so what's to keep somebody from writing to it,
Yeah.
even if they shouldn't?
Yeah.
By the way, Luke Manis has a solution for that, but I'm not going to say it because it's for Grass Valley product. But I got to brag on him a little bit. But there is ways to solve that problem. But it is very much a very real problem because there is nothing keeping from somebody, either from incidentally or purposefully, breaking that API and breaking that connection. So that's quite a big catch.
What was the power load for building that
facility versus what an SDI was?
Fun question. Not better.
Right.
So there's interesting thing to talk about, and I'm going to go just a few minutes over on just because I explained this. Hope you guys don't mind, but it's actually a good topic to talk about. Interesting thing to talk about is called power density. So I said earlier that I can do the functionality of an 800 by 800 SDI router in a 1 rack unit 100 gig switch, right? They use the same amount of power. One happens to be in a 36 RU frame, one happens to be in a 1 RU frame. Now, don't get me wrong, there's some deltas. This is a blanket statement. And anybody can sit down with a pen and paper and prove me wrong, and you're absolutely right. This is just dealing with generalities here. What we're finding is as chips get smaller and smaller and smaller, transistor size gets smaller and smaller and smaller, they use less power. But now, instead of having a million transistors on a chip, I have a few billion transistors on the chip. And as FPGAs get more and more and more powerful, I no longer have an FPGA that's just embedding audio and video. I now have an FPGA that can embed audio and video and do J2K and do H.264 and do command and control and do PTP and do video encode decode and. So even though technology is getting smaller and using less power, because it's getting smaller and uses less power, we're asking it to do more things. So as it's getting smaller, the power density is getting larger because we're starting to do more and more and more. The first SDI router I ever saw that was in a big scale was a Pro-Bell router at DirecTV in Los Angeles. It was a 1,000 squared SDI router, took up 16 racks. At the end of the SDI days, we can do 1,000 squared in 1 rack. Same functionality, same power. I can do 1,000 squared in just a couple of racks now, same power. So your power footprint is definitely not getting better. And the other thing that eats up a lot of power is SFPs. Because SFPs either have LED transmitters or laser transmitters. The lasers really chew up power. You think, well, what does a 2 or 3 or 5 watt SFP matter? Who cares? I've got 1,400 sources. Each one has 2 transmitters, so that's 2,800 SFPs. 5 watts times 2,800 starts to add up. So power and cooling is just as much of an issue as it ever has been. The difference is we can fit it in a much smaller package now. So the amount of racks that we can do a facility in went from 30, 40, 50 racks to do this facility. We could have done this facility in probably 12 if we really wanted to. They just had more space than they ever needed. So, any questions? By the way, as power goes up, air conditioning gets just as bad because you have to cool it. So it's big concerns. So the next was the challenge, and this is an interesting one to talk about. Because remember the last one I told you, we started it about 5 years ago, and it took us a couple years to get on, mainly because the building was being built. But we had to kind of find all these problems and solve all these problems as we went. From the day the customer said, let's buy it, to the day it was commissioned was 3 months. That's the difference a year and a half makes. And it's not the year hasn't changed that much, it's changed a little bit. But what we know changed a whole lot. We know how not to do things. We know how to do things. So notice some of this is pretty similar. So in 71 Cisco, they went Arista. Now they were straight 2110. They didn't do TR04, they did 2022.6. This is a straight SMPTE 2110 build. They still had to be mixed with reference because there was some old stuff that required blackboards. That's going to be around for a while. This customer actually did UHD. It wasn't one of those customers that wanted to spend a whole bunch of money because they might do UHD. This customer needed to do it. So that was a big difference. So because of that, remember, if you have 1,000 sources and you only do 1.5 gigabit, that's 1.5 terabits of storage, or 11.5 terabits of bandwidth. If you do it UHD, it goes up by over a factor of 10. So you spend a lot more money on switches and bandwidth to do UHD. Thankfully, switches are cheaper and faster than they've ever been. So this site had to do HDR, 8 simultaneous productions. So you're starting to see some similarities here. They had to do 8 simultaneous productions, as much IP in the edge as possible. By the way, the first job, the WCAU job, about 70% of that job was native SDI. We just converted it to IP. This job was about 80% pure IP, only 20% SDI. That's the difference 3 to 4 years next. IP switchers. Notice the last job was SDI switchers. Big multi-viewer, 916 inputs feeding 80 displays. As a good reference point, a lot of these IP builds, especially multi-viewers are chewing up between 50 and 70% of the bandwidth on the network. It's not the sources and destinations. It's feeding the multiviewers. So, and think about that if you're feeding multiviewers at 12 gig. It's a huge amount of bandwidth. Another part we're going to dive into a little bit is flexible FPGA processing. They wanted the part that's interesting is this is how we're actually using new workflows with new technology. This customer wanted to be able to do a build or do a show that was 8 cameras, 1 switcher, small multi-viewer, 1 day. Then they wanted to take that little kit, plug it into another switcher or another kit, and now I'm doing 16 cameras with twice as many multi-viewers. Then they wanted to take a third part, put it together. Now I'm doing 24 cameras. Now I'm doing more multi-viewers. What they wanted, instead of building one huge facility, they wanted to build a whole bunch of little ones. So when they needed to go big, they tie them together. When they wanted to go small, they kept them small. So this is a really innovative way they did to do it. And you'll see this. This is just a theme. The operators can't know what we're doing in the background. So this customer was Arista. Now they didn't do the leaf spine architecture like the other customer did. They did just a big switch in the middle. Because it's a truck. You can spare this. You don't need to distribute things all around the truck. But here's the part that the customer brought to the table. Is they wanted an FPGA accelerated platform. I know from the people in this room, everybody here's made a card that does one thing at one point or another. Who here's made a card that takes audio and embeds it on video, and that's all the card does? Or who here's made a card that is a frame buffer, and that's all it does? Or an up-down cross converter, and that's all it does? Well, the customer came to us and says, you know what, I need to buy some IP gateways, SDI to IP and IP back to SDI today, because that's what my requirements are. But I know in 2 to 3 years, I'm not going to need those gateways. All of my devices are going to be IP in 2 to 3 years. So why would I spend hundreds of thousands of dollars buying gateways today just for 3 years to write them off the books? So I want those same cards with different licenses to become a multiviewer, or the same cards to become an up-down cross converter, or the same card to become a frame buffer, or the same card to become an HDR SDR processor. Why not? What's in common with all of those? Big FPGA, ARM processor, bunch of RAM, and an IP to SDI conversion. Why not put it all in one card? So what we're seeing now is this is a trend. This isn't a Grass Valley thing. I'm not plugging Grass Valley because there's other vendors that are doing this too. Is the moving away from purpose-built bespoke hardware to FPGA accelerated platforms. This was our first job that we did where the entire facility was built as an FPGA accelerated platform. Every one of the cards they bought can do everything I told you today just by changing the software license. And very much to the point on power, those FPGAs use way more power than they need to because we need that much more flexibility. But the customer's need for workflow flexibility was enough to justify the additional power. So it broke into 3 designs: broadcast center, remote flight packs, and mid-sized production truck. So this is their production center. So notice again on the other drawings, you had 2 switches and then a whole bunch of other switches below them. They said, you know what? We're in one big facility, or one facility, but not a whole lot of physical space. So they went with what we call a monolithic frame. So there's your X, there's your Y. One of those frames, by the way, I think is 600. Yeah, so I think that one can hold up to 640, 100 gigabit ports on that frame. That's more bandwidth than anybody will ever use. So that wasn't an issue. So they're actually very, very short filled. They've only got 5 36 port 100 gig ports in there and 136 40 gig port. So those frames are really short filled. So things this customer did, you'll notice this is a pattern. There's 2 customers in a row that did that. They used 2 different PTP sync generators. They're no longer sole sourcing vendors for their reference. So you can, why not? And everything was IP connected. There was no SDI in this facility for interconnections. The switcher was all IP, multiviewers were all IP, processing was all IP. The only SDI you had was at the very edge, just to convert it to IP as quick as you could. So the remote site was actually built of 4 different fly packs. The larger fly packs, big IP switcher, big IP multiviewer, a pretty big switch, you notice, 2 different sync generator manufacturers again, and control servers. This site's a little bit smaller. Fly pack 3, you notice, is a whole lot smaller. And fly pack 4, we've just gone down to a little 1 rack unit switch. I say little, remember 1 switch on these at 100 gigabits is still 800 by 800 and cross-point bandwidth. So this is the part I told you where they can take each one of these individual packs, put them together, and make bigger ones. And then they had a mid-sized truck, which you notice these are all very similar architectures. This was a reference design. We did this reference design once for all of these, and it is applicable to all of them. If the site had to get bigger, we just did a bigger switch, some more bandwidth. If they needed less scale, we did a smaller switch that was cheaper. This is the same design, just literally copy and pasted from every single facility. So this is some of the things where doing new workflows buys you a lot of stuff. This saved the company boatloads of money if they only have to design it once and clone it across multiple facilities. This saves them a boatload of money if you can use a smaller switch than you really need. So there's a lot of areas where by using this workflow, they save a ton of money. So the one thing that we found with this problem, or with this truck, was, and this is where SMPTE2110 is really, really a pain in the rear. And for anyone here who's on the SMPTE things, I'm not saying anything bad about you, it's just how the technology is. Remember SMPTE2110-30 was all about audio trunks. So remember I showed you that slide earlier where we had 16 channels in one trunk or 8 channels in one trunk? It's super inefficient to do mono-level audio transport in SMPTE2110-30. I'm not an FPGA engineer. I'm sure I know there's a bunch of FPGA engineers here. They can tell you how wasteful it is to have to in terms of gates, to generate a mono SMPTE2110-30 stream. So in this case, you're going to have 16 IP addresses for every source for audio. It's a very inefficient way of doing it, so we don't. For the most part, most facilities go down to 4-channel trunks. So to get to 16 channels, you do 4-channel trunks, you get 16 channels of audio. So here's the problem. Say you have a replay server, or any server. Let's say you have this little, is that a keypro? Whatever that, okay. So say I've got a keypro that's IP. That keypro needs to record a video and needs to record 16 channels of audio. The first 2 channels of audio need to come from the audio board. That's your program preview, or your program outputs, left and right. Maybe your next 2 channels of audio need to be ISOs from some cameras. And those next 2 channels need to be ISO from another camera and another camera. So now we have 4 different sources of 4 different audio pairs which will require 4 trunks. Well, if the device only can handle 1 trunk, how do you get mono-level audio routing, because we still need it, into a device that only allows you 1 trunk? You can massively oversubscribe. You can make the device so you can subscribe to 2, 3, or 4, or 5 audio trunks. What happens if you need to subscribe to 16 channels because you've got 16 different mono audio channels from 16 different sources? What do you do? So we literally had to create an all IP audio router. So a mono-level audio router in the IP domain. So for the audio guys in the room, everything you know is still just as important today as it was in the past. Because we needed mono audio level routing in the SDI domain, we still need that workflow here. The workflow hasn't changed. We just need new tools to adjust to the workflow. So on the Grass Valley side, we created a product called Audio Live. And it's a 1 rack unit server that can subscribe to just hundreds of AES trunks, do the audio routing, and spin them back out in the predefined trunk that it needs to be. We didn't really foresee this until we started that job. But you notice this is all that we had wrong with the facility. Now granted, it was another couple man years of work we had to do really quickly to fix it. But this job was significantly easier than the previous one. And you guys may have seen this slide before, and this slide is more relevant than it's ever been. It's true. Half the time, I'll reboot it. Well, it got redundant XY network, so they're actually not going to take you off the air for doing it. Or maybe the code is bad, let's update the code. Again, you've got XY networks. Update Y, leave X as it is. If Y seems stable, then fail over and update X. You know, there's all sorts of tricks we can do to keep everything up. This is more relevant than it's ever been. So this is the last slide I got. And you're going to see this has been prevalent through the entire presentation. This job went so easy because their engineers knew their shit. And there's no other way, more gracious way for me to say it, my apologies, but their engineers were just top-notch. They had fantastic IT guys. They had fantastic broadcast guys. The problem was it wasn't the same guy. They doubled their staff to make this work. that's actually not very cool with a lot of our customers. And this comes back down to spend the time with your engineers, with your managers, with your company, with your customers. Spend all the time you can training and learning and trading knowledge. Because this has been the deal. Yes, you can fix this problem by hiring twice the engineers. But now we just added $1 million and maybe $1.5 million to the payroll we didn't have before. And that's going to be on there every year. So we need to train the unicorn. The unicorn is the person that understands SDI and the workflows, as well as they understand IP, as well as they understand SDN, as well as they understand all the emerging technologies, but has the drive to learn what's coming on next. That's what we need to be training. We call them unicorns, because in Grass Valley, when we find them, we love to keep them, but they're hard to find. So, that's what I got. Thank you very much.